Okay, welcome to lecture 5. Today we're going to go on. If you remember, the last recorded lecture we had was on the Budworm model, where I said it was a model that actually provided a switch. It was a model that had 2 parameters in it, and when you have 2 parameters that can move your fixed points, you have different possibilities than if you just have one. In lecture 3, and we looked at bifurcations, where we basically studied all the normal forms or all the possibilities if you just have one parameter. Last time we introduced 2 parameters, and what I'm going to do for the first part of this lecture is go on and actually study what attributes you can get if you have 2 parameters. Remember, we have the result in one-dimensional systems that because we're restricted to moving on a line, right? X can just increase or decrease depending on what the v dot is. You're either going to go to a fixed point or you're going to go to infinity. And what the parameters do is they basically change the fixed points you can go to. They can change the nature of the stability of the fixed points, but that's all. And so when we study a 2-parameter system, we're basically studying how the parameters are changing the natures of the fixed points. And so the system we studied the last time was this Budworm system. And we took a lot of trouble in reducing the original model that had 4 parameters in it to a model that has just these 2 parameters in it, where R is our scaled carrying capacity, and K is our scaled carrying capacity, and R is the dimensionless growth rate. Okay, and R, you know, when they speak of all these COVID things and your R naught value, and that was the reason for the lockdown, what they're talking about in that R naught value is basically the growth rate, the way the thing transmits without any other inhibition. So basically how rapidly, if you have one COVID positive person, how many it can infect around it. And that R value plays very much the same role as what this R value plays here. It's basically the reproductive rate. Okay, and that happens in any model where you have something that grows and other things interact with it. And it also means that if X is small, the model basically has, any model has exponential growth. So we were so afraid of exponential growth with COVID, but the truth is, when you start growing in any medium, if you're growing bacteria, if you're growing a virus, you always initially have an exponential growth. Okay. And anyway, you can choose how fast that growth is, and that's what we try to do with the lockdowns, is limit how fast or how many people were in our hospitals or are in our hospitals. Okay, so this model came from that outbreak model, and remember the story, the physical story is you have these worms that eat the foliage of your trees. Usually it's fine, the birds eat the worms, but then something really weird happened. Suddenly you have this explosion of worms suddenly appearing. They eat all the leaves of the forest, and the forest dies. And it was a very real and expensive problem to try and find out what to do to stop this. And so there were people that were doing forestry that said, well, if we breed the predators, if we have like the special breeding program for the birds that are the predators that basically enter into this part of the model, then we could maybe breed the birds, and then the moment we see the budworms come above a certain level, we introduce the birds so that the birds know that they eat the budworms, and we can save our forest. So it was a very real problem where the model came from. What we're going to do today is simply study the mathematics of the model. Okay. So the first thing we do always, and this we did last time as well, so if you want the detailed version, go to the previous lectures recording, is we find the fixed points. I mean, this is true for any model we're finding the solution of. We find the fixed points. We solve the case when f of x star is equals to 0. And we immediately see, because x multiplies in here, one of the fixed points is x star equals 0. And you must always put in the parameters for which the fixed point is valid. And so you have, and that's true for all k and r. The next fixed point basically obeys this thing. Okay, and so it's basically R times this term, I've basically just removed the x or divided out by x. So it's basically this equation that it obeys. And you can see if you multiply through by the denominator, you have a cubic equation. And a cubic equation can have 1, 0, 1. So it'll always have one root, because it goes from minus infinity to infinity. It can have one root, it can have two roots, or it can have three roots. So what we study when we study the dynamics is how these roots change as the parameters of R and K changes. Okay. And the last time, and I'll talk a little bit more about it, we derived a parametric expression for R and K where the bifurcations occur. And remember, we said to get that parametric equation, we solve the equation f of x star equals to 0 and the derivative of f of x star equals to 0. And then we have two equations. We have three unknowns, in other words, r, k, and x. And so we can basically write r as a function of x and k as a function of x. And then we could find that the minimum value at which k achieves to get a fixed point is this 3 times the square root of 3. I'll show you how that arises again later on. Okay, and that's true for all r. Okay, and we also found for large k, we could have 1, 2, or 3 fixed points. Remember, I had this picture of where the k and the r changes the line, and the k was large. I'll show it to you again in a moment. But we could see that there was either 1, 2, or 3 intersections in the graph. And if you had 3 intersections, it basically meant that if you drew your diagram of f of x, the phase diagram that we've been looking at in the past, you had this equation, you basically draw this equation on the graph, and here you have your one fixed point at 0, and this is the case where you've chosen k and r, that you have 3 fixed points. And just to get the terminology straight again, the stable fixed points represent stable populations of insects. So, and this one I'm going to call the refuge population, that basically refers to the population of increased sex where the population is low. Like there's a small population, they're not very active. Then there's a threshold over here, that's the unstable fixed point. And then there is the outbreak level of insects. So when you have 3 fixed points, your model actually predicts that either you can be, depending on where you start, so say you start breeding from 0, you're going to end up there. You're going to be in the refuge population that doesn't bother anybody. But say, for example, somebody comes secretly at night and releases a whole bunch of insects, that you have so many insects sitting over here, then that whole population is very quickly going to go to this outbreak of level of insects, and it's going to eat all your forest's trees. Okay, so just when I'm talking later on of your refuge population and your threshold and your outbreak population, I want you to know that they are actually labeling fixed points. Okay. So the other thing we did last time, and this is just a little bit more of review, we said that the bifurcations occur, and this is true for any bifurcation, when you are at a fixed point, because we're only studying the bifurcations of fixed points in one dimension, and the derivative of the fixed point is 0, and this allows you, as I've said, to parametrically define the bifurcation curves. And what we derived in the previous lecture is basically, if you solve f of x equals to 0 and f derivative of x equals to 0, you basically eliminate r and k, you can write that r of x is equals to this parametric equation, and k of x is equals to that parametric equation, right? We have 2 equations that start from these 2, and we just solve for r and k in them. And then the place where this number came from is that you can then say, plot what these curves look like by plotting it parametrically. And remember, the last time I said, when you do that, you basically look for places where k goes to infinity, in other words, where x goes to infinity and where x goes to 1. Those 2 will give you sort of infinite places where k goes to infinity. You put that on your graph. you work out what R is there, and then you plot them. You also work out what happens when dr dx is equals to 0. You put that point in, and then you plot the k value there. And that's how we drew that parametric curve. And you'll see it again on the next slide. It sort of was this thing that kind of looked like that, if you remember it from from lecture 4. But I'll show it to you again. And that was just drawn from these parametric things. Okay, so that's sort of where we stopped the last time. What I'm going to do now is introduce the terminology that arises in these 2 dimensions. Because even in this relatively simple dynamical system, you can get fascinating physical phenomena out. And the first thing you can get out is a thing you call hysteresis. Okay, so how many of you have studied physics? Okay, so if you think about hysteresis, the place where you've seen it is when you have iron, right? Iron is not magnetizable. Any piece of iron is not necessarily a magnet, okay? But if you put it near a magnet, it'll stick to the magnet. So what happens if you want to make a permanent magnet? You basically put iron that's not magnetized in a magnetic field, and you increase the temperature, okay? You increase the temperature to a certain height, you keep the magnetic field on, and then you will leave the iron there, and then you decrease the temperature. And then when you decrease the temperature, you'll find, and you switch the magnet off, you'll find that the magnet that you put in there is actually magnetized, and it stays magnetized. Okay. If you happen to drop the magnet or the scissors, then you lose the magnetization. But this idea that you can have an object in one state, do something to it, and get it to another state that it's stuck is an example of hysteresis. Okay, so the mathematical definition, or that we're going to say, it's basically a lack of reversibility with respect to slowly changing or drifting parameters. So in the example of iron, you have the temperature is your parameter. The moment you push it over the Curie temperature, you can magnetize it permanently. And when you take it down, you don't go back to the unmagnetized state. Okay. It's exceedingly useful. Transistors that you have also make use of hysteresis when they use the switches in computers. Okay, so there's a lot of application of this very, very simple idea. The second thing I want to introduce is the idea of a cusp catastrophe surface. And I'll plot it for you on the next slide, but what it is, it's basically a bifurcation surface. Remember, we've been drawing the bifurcation diagram when we had one parameter. We had x, the fixed point, as a function of r, okay? And we had our pitchfork bifurcation, our saddle node bifurcation, that all had different properties. If you have 2 parameters, so in this model it is r and k, then instead of having a line for your bifurcation diagram, you're actually going to have a surface. You're going to have your parameters on, say, the xy plane, and you're going to have your fixed point on the z-axis. So a cusp catastrophe is something that happens. You necessarily need 2 parameters to get it, so it's not something you're going to get in the one parameter examples. And what it is a bifurcation surface that folds in on itself. Okay, and I'll show you how that arises in the next example. Okay, and the projection of the folds are the bifurcation curves that we plotted just now, or that we plotted in the last lecture. And a catastrophe occurs when you sort of move along this bifurcation surface as the parameters change, and you sort of fall from the one branch of the surface onto the other one. Okay, so the definition of catastrophe is, as the parameters change, the state of the system can be carried over the edge of the upper surface, and it drops discontinuously onto the lower surface. Okay, abstract at the moment. I want to illustrate it on the next slide because I like making the simulation, and it illustrates it actually really, really well. So let's actually look at what we have. So in the end of the last lecture, we drew this bifurcation curve, okay? It's just, note it's a bifurcation curve, it's just in the parameter space. Our two parameters are R and K, and this is the point where, this is the line at which both f of the function on the right-hand side and its derivative are equals to 0. Okay, so that's what we derived in the last lecture. If we now draw the bifurcation diagram, okay, so what does how I drew the surface, it is simply the surface where you get fixed points. Okay, so this surface is defined by the equation of f of x equals to 0. Okay, if you do that, you have one equation, you have three unknowns, so you're defining a surface. And so where f of x is equals to 0, the surface that's sort of indicated by all these pink and red lines is given here. And now what the bifurcation curves are is whenever the derivative of the fixed point, whenever the surface bends, is actually when you get your bifurcation curves. So if you look at this this thing down here is projected onto the parameters R and K, the RK plane. And you can see where it derives from. We got the parametric derivation up here, but what it means is simply the lines on this bifurcation surface where the derivative goes to 0 of f with respect to x is over there and up there. Okay, and when you project that down, you get your bifurcation curve. Questions at this point? Okay, you get a feel that when we have two parameters, you no longer have a bifurcation diagram that's a line, you have a bifurcation surface in 3 dimensions. You plot the surface by plotting the surface of f of x star equals to 0. Okay, bifurcations occur where f prime, the derivative of f with respect to x star, is also 0, and that's basically these purple lines, or the light purple line. If you project that down onto your RK surface, you have this dark purple line, which is the bifurcation curve I derived up here. Okay, so now I want to show you what happens if we solve different problems. So this is what the bifurcation diagram tells you. It's telling you information about the surface on which your fixed points occurs as a function of parameters. The differential equation for a set of fixed points, I'm going to plot its phase diagram over here. Okay, and what I'm further going to do is I'm going to choose K. I'm going to fix K, just for an example. And I'm going to say, let's look if we choose parameters that move along this red line. In other words, I'm going to fix K, so K is a certain value, and I'm going to change R and see what different solutions are possible. Okay. So let's start, and let us choose fix K to 10 over here. We choose R to be 0.3. Okay, you can immediately plot that point on your bifurcation diagram because it will immediately give you a clue of how many fixed points you have. And this is why it's important you should get all these diagrams together, because they allow you to check your calculations as well. Okay, so here's your bifurcation diagram. We're going to start with an R and a K. I'm going to plot it over here on the red line, so there it is. Okay, so when you have those two parameters, you only have one fixed point. Okay, and that fixed point we're going to call the refuge, and that fixed point basically gives you the height of the red line over here. if we look for that particular R and K, we plot our phase diagram. In other words, just simply x dot, which is f of x star for that R and K, what we get is this. Okay, so we can see that our phase diagram represents what we expect from our bifurcation analysis. We've got one fixed point over here. We know and it's the only fixed point that is stable. So we know regardless of where we start, the insect is going to have this value. Okay. The final thing that the final graph, oh, no, wait, let's go back. Okay. The final graph that I have over here is just to make this thing more apparent. So all I'm going to do here is I've got my value of my fixed point, and I've got the value of the parameter of R that I'm changing. So it's just to make this graph over here easier. So what you can imagine is I've basically taken a sheet of paper and I've put it in at k equals to 10, so it captures my bifurcation surface. Okay, so this graph over here is simply this three-dimensional graph where I'm only caring about the surface along the red line. Okay, and it's just to blow it up that you can see clearly what's happening. And so what I'm going to do now is what we're going to study is what happens if we have this population of insects that we know goes to this fixed point, and we slowly change that knob R. What's going to happen to the actual solution? Okay, so now we're going to basically slowly increase R. Okay, that's a parameter in our equation. It is not the solution of the equation. So if you change R a little bit, and you start at the initial condition that was the fixed point is going to move. Okay? So we now increase R. We choose a new parameter in this bifurcation diagram. Okay, so we're choosing new parameters. We're keeping K fixed to 10, and our R is moving slightly closer to our bifurcation curve. So we've moved up from there to there, and we've moved along this curve over here. And you can see what happens to the actual phase diagram. That function we're plotting has moved itself a little bit. The fixed point has changed a little bit, but effectively nothing much has changed. Okay, it's still the same structure. Now, if we increase R slowly again, okay, I've chosen it strategically to be a value that actually lies on my bifurcation curve. Okay, so it lies on my bifurcation curve. Remember, on the bifurcation curve, I know that the derivative vanishes as well as the fixed point. So we have that marginally stable or sort of indeterminate case over here. Okay, it's also the case where I have a saddle node bifurcation. Right, I have a line hitting the fixed point from the top, and what happens there is my threshold and the outbreak, the two fixed points are now born over there, and I can see that actually happening. But because I'm starting my equation in the system, the insect population is going to be there, just stay there. It's not, because of the insect, the initial condition of insects is there, it'll be attracted to that fixed point. It won't know this is really happening. But we're going to carry on. Okay, we're going to change R even more, so we move up into the state where we basically have the possibility of having two fixed points. And depending on where you start, it's going to either be attracted to the refuge population or the outbreak population. But because we start here at the refuge population, the solution is going to stay there. And so now if we increase R even further, we move up along there. So the graph changes a little bit in shape, but the number of fixed points doesn't change. So we still have the refuge population of insects, we still have the threshold, we have the outbreak population of insects. And so even though the threshold is closer to the refuge population, as long as you're in here, you're not going to have an outbreak. And now where it starts getting interesting, you can go up one further and your threshold moves closer to your refuge population. And the interesting thing happens at the next step, right? So now the next one is going to go onto this other bifurcation curve. So at this other bifurcation curve, what we have is our refuge population collides with a threshold. And you have a bifurcation, a saddle node bifurcation that actually just starts destroying this refuge population. So you can see that this thing now is a marginally stable, or it's basically unstable, right? You approach it from this side, it's a half stable fixed point. You approach it from this side, you get stuck. You perturb it a little bit off of that one, like one extra bug, and you're going to run away to a situation where you have a whole bunch of insects. They're going to eat up your entire forest, and you're done, and everybody's miserable. Okay, so when you reach this point, okay, where you effectively have your refuge population's fixed points disappearing, what's going to happen to your forest is that your solution is suddenly going to jump to this outbreak population of insects. And you no longer have the option to have a few number of insects that are stable. Okay, and this jump is when the catastrophe occurs. You've literally moved along the solution surface over here, and then when you reach that point, you suddenly jump up to over there. Your forestry people panic, but there's nothing they can really do about it. And this is what the model actually illustrated. Okay, so it jumps up to the top here. You can now say, suppose you slowly increase your growth rate. You go on, and then all that does, it changes the shape of the graph, but the fixed point simply increases a little bit. You increase the growth rate further, the fixed point increases a little bit over there, and you can just keep going if you wanted to do that. But now suppose you have your forestry people that want to say, oh, we want to manage this. Let's try and find a way to change that knob R to try and make the outbreak of insects that's eating all our trees go away. And this is where the bad news starts. It's not a matter of just turning the knob back to over there. It's a matter of doing a lot more, right? So if you decrease R a little bit, right, you're going to move back along this curve, but you're going to start there, you're going to move back along the curve, you're going to start there, you're going to move back further, you're once again going to have the threshold and the refuge population occurring there. But because your solution is sitting over here at this fixed point, it's going to stay there. Okay, so if you move the fixed point back even further, you're not going to jump back down to over there. You're instead going to start moving along this top branch of the solution. Okay, so you're going to remain in outbreak for a very long time. So even though you've got a threshold and you've got the potential of a solution for a refuge population, you don't get there. You stay stuck. Just like the iron magnet remains magnetized even though you decrease the temperature, there it's a good thing, here it's a bad thing. But the model is the same. So you remain stuck. As you decrease R, this thing changes, your threshold moves. It moves more and more this way, and you just keep going until eventually you hit the second bifurcation curve. And when you hit that lower bifurcation curve, the threshold and the outbreak populations basically annihilate itself. That solution is no longer possible. And only then, if you perturb it a little bit, are you going to jump back to your refuge population and go down. Okay, and that phenomena where you jump around like that is what you call hysteresis. And that phenomena, for the outbreak, it's bad. For iron filings or sort of magnetizing iron, it's good. For Master KG, with his famous Jerusalem dance thing, it's a similar model, right? If your R growth rate is basically if one person, what population is. If one person sees the video, likes it, how many times does he retweet it? So most videos sit here in the sort of, they're just interested in South Africa, right? Then something, but they're good, so the popularity increases. And then eventually here you get somebody that's famous or somebody that does something cool with it. It tweets and suddenly it goes to outbreak level, right, where it's really, really nice. And then you'll have to do a lot to stop that and make it go back down again. So basically, if you apply this type of model to YouTube videos, it basically means it's hard to get famous, but once you're famous, you tend to stay there until something really bad happens or people become very, very forgetful. So this type of model of having hysteresis is, you see in many places. This is one of the simplest examples where you can get it. And it's actually physically very, very useful. Any questions? Yes?
When you increase that point on the bifurcation curve from the bistable to the line S1, when you increase it from that region to line
Yes,
S1,
yeah.
the number of fixed points from the phase diagram changed from 3 to 2.
Okay, let's just go. So you're talking about there.
Yes.
There, yeah.
There to that line, the number of fixed points changed from 3 to 2.
To 2, yes.
I think you mentioned that it's a certain bifurcation.
Yes.
Could you explain how that?
Okay, so whenever you have, so remember we looked, it's saddle node bifurcation in R. Okay, because remember I've fixed K. Right, I'm only exploring the thing where K is a constant. A saddle node bifurcation, remember when we studied in just one dimension, I said it occurs whenever you form a pair of fixed points. Okay, in other words, when from nothing you get a stable and an unstable fixed point.
In that case, we have 3.
Yeah, but I'm talking just locally, right? So the one fixed, so we actually have 4, right? This one is stable always. Okay, this one is stable, but whenever you do that, where you have 2 fixed points being born, you have a saddle node bifurcation. Remember the way we said with a saddle node bifurcation, one way of looking at it is you do a local analysis. You go to the fixed point or the bifurcation point and you make a Taylor series expansion in your X near the fixed point and your parameter R. Okay, and if you do that, you're going to get that normal form. I think it was in lecture 3. You're going to get that normal form, and it has a certain shape. Okay, or it has a certain parameter entering it. And so the reason I call this thing a saddle node bifurcation is if I take that very complicated function of f, okay, and I go to that fixed point and that parameter, and I expand around that fixed point and parameter, the normal form I'm going to get is the saddle node normal form. Okay, so the bifurcation is basically labeled by a local analysis. Okay, just for example, that example we had in the tutorial test where you had your sine function and then you had the line going down. Okay, wherever that line hit the curve and you had 2 fixed points being created out of nothing, you were doing a saddle node bifurcation. Okay, so the saddle node bifurcation results from a local analysis. The other type of bifurcation, like the pitchfork bifurcation, there was one place where you had a pitchfork bifurcation in that example, and that was on the axis. Okay, there also you could look at the problem, go to that fixed point at the bifurcation parameter, do an expansion, and you would get the normal form of the pitchfork bifurcation. Okay, so when I label a bifurcation, I'm talking just about the region very, very close to where the transition occurs. Okay, and the reason I do that is because I've labeled it using the Taylor series expansion at that bifurcation point. Okay. You could have a system that has both, that has bifurcations. If you have two parameters, you can have two kinds of bifurcations happening at the same time. You know, for example, if you were to take that sine curve and just move it down with a parameter, you could have several saddle node bifurcations happening at different points for the same parameter. Okay. Other questions? Yes?
Now, on the bifurcation and the other bifurcation diagram in 3D,
Yes.
what happens at that place where, like between those 2 points? Yeah.
There.
No, not that. It's those 2 points that we basically do where the jump occurs.
Yes.
Yeah. What happens? Yeah. Where there. Yeah. Precisely there at that particular turning point.
Oh, at this particular turning point. So here we have where the jump occurs. At this particular turning point, so let's just go on. That particular turning point, okay, so we're going to go, let's go back. That particular turning point over here becomes important when you're decreasing R, right? When you're decreasing R and you're now stuck on the top surface. So when you do that, you're moving down that bifurcation surface, and that where it goes vertical is where it jumps down. So it literally falls. That's why they call it the Cusp Catastrophe. It literally, as you change your parameter, it falls from the one solution surface to the one below, and you force that falling.
So the curve beneath that, like it's that point. Then, so what about the slight curve beneath the turning point?
You mean this one?
What's its significance in that?
That one is referring to this other turning point over there is where your threshold occurs. Okay, so remember, it falls down then to the lower solution surface. Okay. And it's going to fall to the lower solution surface. This other part of the curve, remember, it became important. It's this lower one. When you increase R from, say, 0, you move along this lower surface because you're stuck on it. You move, up to, you get to that end of the surface over there. Okay, when you hit that, you once again are on the bifurcation curve S2. You then jump back up to this top solution surface and then go down.
It's that place between those two jumps that I want. Let's assume that it was basically at that point where it jumps the point. Yeah,
this point.
Yeah, let's assume it was there. What happens between the place between that particular point where the arrow is and where the turning point is? Like that slight.
Do you want me to?
Curvature up, so to speak.
That slight curvature up gives you what the fixed point value is. So this slight curvature up here you're talking about.
Okay, this one is.
Do you want to come and draw on the board? You're welcome.
It makes a curve like this.
Yes.
Then it does this.
Yes.
Yes, this part I get. It's basically that it jumps below that point, and there it basically goes to an outbreak.
Yeah.
What I wanted to know is
what happens there?
This particular curve, because I can't quite account for this.
Ah, but you can. That's a good question. That part, when you draw that curve, remember this curve that you've drawn? It's fixed points as a function of parameters. Okay, so what makes that curve that you've highlighted over there important is that you must actually do this. Right, if you were to draw your bifurcation diagram correctly, this branch over here is stable. Okay. this is unstable. Okay. So what that branch does over here, that curve, your fixed point, your actual solution never gets stuck there. It's the unstable branch. And the only thing its use is, it's basically this point, this threshold point that separates the region that goes from the one fixed point to the other fixed point. Okay, so suppose you chose these parameters for your equation. And suppose I said, I didn't tell you what the initial condition was, but I suppose any initial condition, I chose any initial condition to the right of the threshold, then the basin of attraction of this solution is this region, like from 3 to 0. Anything that you start there will go to that fixed point. And that curve that worried you is the unstable branch. It separates this basin of attraction from this other basin of attraction to your outbreak level. So if you happen to start your differential equation over here, it'll stay in this region and it'll be separated by an unstable branch. Okay. Very good question. Thank you. Okay. More questions before I go on? In fact, I'm not going to go on. I'm going to stop here. Yeah, I think it's a good place to stop. I will do linear systems the next time because it's a nice long story and I'd like to do it properly. But yeah, thank you.